Good morning. My name is Aditya Venugopalan. My student ID is 1899824, and this is my presentation on hybrid modeling on radio frequency and FSO signal attenuation. In this talk, I will walk you through the motivation, methods, implementation, and evaluation of a data-driven approach to predict signal attenuation in hybrid optical radio frequency communication systems under varying environmental conditions. Modern communication systems face signal degradation due to atmospheric disturbance like fog, rain, and turbulence. Free space optical FSO links are especially vulnerable, and while radio frequency signals are more robust, they have lower bandwidth. Combining both forms a hybrid system which demands accurate modeling of attenuation under dynamic weather conditions. Traditional physics-based models often fall short in handling nonlinear patterns and multivariate weather conditions. This is where machine learning comes in. Our objective was to develop models that accurately predict FSO and RF attenuation levels using environmental parameters as input. The challenge lies in dealing with real-world weather data, which is noisy, skewed, and highly imbalanced across conditions. We aim to build interpretable, generalizable models that support real-time decision-making in telecom, aerospace, and defense communication networks. We had three goals. The first was to evaluate the performance of general models versus sign-up specific models. Second, to explore the impact of feature selection and hyperparameter tuning. And finally, to test if a hybrid two-step model using predicted radio frequency attenuation can improve FSO predictions. This work has practical applications in developing dependable hybrid radio frequency FSO systems. Now, understanding a dataset on which the project was built. Our dataset contains 27 variables, including temperature, dew point, visibility, pressure, wind, speed, and various cloud and turbulence indicators. Two target variables are FSO attenuation and radio frequency attenuation, which were named as FSO underscore ATT and RFL underscore ATT. Additionally, the dataset also consists of the sign-up code, is, which is a categorical identifier for local weather stations useful for local specific modeling. Sign-up code explanation. Sign-up codes help us to segment the dataset based on religion weather patterns. By training per sign-up models, we allow model to learn from region-specific environmental interactions. Later in this project, we evaluate how effective this approach is compared to a global model. Distribution and class imbalance. We noticed a major imbalance in sign-up code distribution. Some weather stations had thousands of samples while others had only 50 samples. This imbalance could be bias the model toward overrepresented stations. Downsampling and balancing. To correct this, we perform bootstrap unsampling of minority classes and downsampling the majority, capping each sign-up code group around the median count. This improved the model fairness and generalizability across weather conditions. Correcting skewness. As we can see from the information related skewness, we can see particulate max, particulate min, and rain intensity max, rain intensity min, wind speed max, and wind speed min have high skewness. These are the features in present in dataset which tell us about the environmental factors and their capacity. These features indicate most of their respective values are clustered on the left-hand side. Applying the transformation will help to normalize the distribution and hence improving the model performance. On the other hand, the feature relative humidity show negative skewness. Since we haven't done feature selection process, we will include this feature and hence transform relative feature as well. After applying the square root transformation and power transformation, we can see the difference in the skewness, as the skewness have now comparatively decreased, which will help us in our model building and giving us more accurate prediction. Now, before before I jump into data splitting for model training, I will really like to uh, point out the fact that we also had done outliers removal. Since it's we can't show it on the screen since few outliers were purposely kept in the data set for model buildings because these outliers could possibly be some values that could present some extraordinary cases. So the post-removal in the outlier removals, we saw a significant tightening of feature distributions. The box plot showed clearer boundaries, which reduced the noise and variance during the model training. This was critical before doing test selection. Now, train testing splitting. We performed a 70-30 train test split, ensuring both FSO and RF intervention models were trained and evaluated on the data. Stratification was done per sign-up code where needed to treat imbalance. To build accurate predictive models, we split our dataset into training and testing sets. This ensures that model learns from one part of the data and evaluates on the unseen data for fair performance measurement. Training set used to fit the model and testing set we use to check the model accuracy. Now we will discuss how general models and sign-up per sign-up models were built. The general models, we built two general models for RFL and FSO. You might be seeing RFL and RF a lot of places in my presentation. Please don't be mistaken, they both mean the same thing. Anyways, coming back to the presentation. So we trained two baseline random forest regressors using all the 27 environmental features to predict the radio frequency attenuation and FSO attenuation and out of bag validation score, which is also called as OAB score. This gave us a quick estimate without separating the validation sets. We removed the target variables FS attention and RFL ATT and used all the environmental features. Initially, the data was split into 80% training and 20% testing to validate model performance. Later, we will change the ratio of the training and testing split, which will be explained later. Coming back to the general models, we used random forest regressors and 100 estimators and enabled the OAB score. Performance evaluation. We measure the RMSE, that is the root mean square error, to be um, 0.7845 for the FSO model and 0.4901 for the RF model, that is the radio frequency model. And for the R square, it was 0.9590 for the FSO model, while it was 0.9797 for the RF model. Basically, the lesser the root mean square error, the better it shows the accuracy, while the R square should be closer to 1 to indicate the better model fit, and the OAB score is used to measure the model generalization. So if we compare the models, we can see that the FSO model has higher RMSE, meaning it struggles to take more attention accurately, while the radio frequency model has a lower RMSE, making it more precise. The R2 squares are high for both models, which means they explain most of the variance of the signal attenuation. Overall, the RF performs slightly better than the FSO. While the FSO predicts more uncertainty, it is likely due to weather impact. And before we proceed to feature selection, we did a downsampling of the data set. The reason why we did a downsampling, as we can see, our data set had a lot of variables in it, a lot of features in it. So to make sure the data set is a bit balanced and not biased, we did a downsampling. Now coming to feature selection. The feature selection was done on the method called as background elimination. We applied backward elimination using the OOP score, which is out of bag score, and RMSE as evaluation metrics. The least important features were removed one at a time, and performance was tracked. The optimal point was when RMS began to increase. Now, the once we did the feature selection, we did the feature selection on the models, on the generalized models for RF and FSO. We got the following output. We can see that for RFL attention, we got 16 out of 27 features, while for FSO model, we got 14 features. The feature elimination improved the model performance and reduced the training time without sacrificing the accuracy. As we can see that the MSC has reduced more, and we means that we have got more accurate predictions, and we got a high R squared, which means a strong correlation between the input and the output. When it comes to OAV, we can see it is now generalizing more. On the other hand, for FSO models, we can see the same pattern, which means the RMBC has decreased, the R score has increased, and the out of bag score shows that it has shown a strong overall performance. Now, coming to the general model performance evaluation, now we'll compare the general model performance and optimized model performance. So we can see that the radio frequency model performed better than the FSO model with lower RMSE and R square. The free space optical model had higher RMSE, meaning more variation in prediction. Both models had strong OEB scores, meaning they generalized well. Conclusion: the radio frequency model gives more stable predictions, but the FSO still captures key variations. Now, now talking about per sign of model and performance analysis. We trained individual models for each sign-up code. Remember, initially I had said we had 7 sign-up codes. Instead of single general model, different weather conditions impact different. So we created custom models perform better. Key findings now. The best sign-up RF model achieved the RMC of 0.29, while others range up to 0.9. The FSO models also vary. RMC and R square fluctuated widely, confirming that the local weather behavior varies across the stations. I would like to repeat the key findings since it's very important for us to understand what happened here so that we can proceed. Some sign-off models had very low RMSE, which means it had better accuracy. R square are near 1 for some models, while meaning it means excellent prediction. See the O out of bag score to confirm the model generalized very well. Now comparing the general models for sign-off models. Before we even compare, we need to make sure that why are we even comparing. So general models trained on weather are trained on all weather conditions, while the post and models are trained separately for each weather condition. This helps to understand if specialized models improve the accuracy. And now, time for the results. Now we can see that uh, the RMS, the best sign-up RF achieved the averaging across sign-up. The radio frequency RMSE was 0.54, the FSO RMSE was 0.93. You can see the average score is a bit different, which means that the general models were very close. However, some sign-on code benefited from the local modeling. This to justify a hybrid approach in later steps. Remember, this was one of our aim for and for building this project. So we can make following observations that per sign of radio frequency models have low RMSE and more accurate predictions. Per sign of models show better OAB score, which means they generalize better than general models. And FSO models generally have higher IMC than our radio frequency models, indicating they're more sensitive to weather conditions. Now it's time for hyperparameter tuning to get the best parameters for our models. So before even I explain the results of the hyperparameter tuning, I would love to explain why we did hyperparameter tuning. So hyperparameter tuning helps us to find the best settings for random forest model. It improves the accuracy by optimizing the parameters like tree depth and field selections. So now what happened? So we use randomized search CV to test different hyperparameters. The best parameters found were 500 trees, max up of 20 n squared for the feature selection. And now the new model string were using these settings, we got the results. The RMG improved to 1.03, 38, which means it had better accuracy. The R square was 0.9613, which means strong predictive power. And the out of bag score was 0.9608, which means the model generalizes very well. Now it's time for hyperparameter tuning for the radio frequency model. Now, for the radio frequency model, we got the following results. The RMSE was found to be increased, improved, and had a better accuracy, which means it had a better accuracy, that is 0.8758. The R square was turned out to be 0.9233, and the out of bag score was 0.9229, which means strong generalization. So we can see that doing hyperparameter tuning for both of our models, we got better parameters. And now, time for comparing the radio frequency and FSO models after hyperparameter tuning. So we can see that once we compare the optimized radio frequency and FSO models in the two main metrics, that is the RMSE and R square, we can see that the radio frequency model has lower RMSE, meaning better prediction accuracy. The free space optical model has slightly better R square, showing strong correlation with the target variable, and both models perform very well after hyperparameter tuning, showing balance improvement. Now time for um, measure versus predicted RF attenuation. So in method 3, we predicted radio frequency attenuation in the first, and then use it as input to the free space optimal. This created a hybrid learning pipeline where radio frequency served as an intermediate signal for frequency on the, which on other hand, like in easy words, so what we did in this step is like we created a radio frequency model to predict the radio frequency attenuation using the environmental features, and we got the following RMSE, R square, and OMB score. You see, the RMC turns out to be 0.7870, the R square was 0.9381, and the OMB score was 0.9317. And if you look at the scatter plot, you can see the points are very close to the red line, which means it has better accuracy, and it compares the actual versus predicted line, and its most prediction aligned well, confirming a strong model fit. So now we have a new model which is used to uh, predict the radio frequency attenuation. Now we'll store it as a feature so that we can predict the FSO attenuation using this feature. And now we will make a predict FSO model with RFL as a feature, the predictor RFL as a feature, and we'll see how the model works. So now, as we can see that uh, we a random forest was trained once again, and it was tested with this new feature, that is the RFL feature, and we got the following RMSE, that is 1.4438, that is higher than the general model. The R square seems to be very low, and the overall score seems very average. Now, the conclusion of this um, step was when we predicted RFL attention, it did not improve the prediction of FSO attention, and further hyperparameter tuning of feature engineering is required, which means that even though we added the predictor RFL attention, the performance did not improve for the FSO, which could likely be caused due to compounded error from the predictions, which means that RFL has not very much influence on FSO. Now we will check the correlation between the RF and FS attenuation to prove our theory. As we can see, the peer correlation between the radio frequency attenuation and the FSO attention is minus 0.42, which means almost no linear alienation, and the mutual information score is 2.4004, that's very weak non-linear independence. We tested if using predictor RFL as an additional feature could improve the FSO predictions. It turns out to be a big no, which means that the performance worsened, and the higher RMSE and lower R square compared to the alternate FSO model also supports our theory. Since our first theory fails, now we will do feature selection on each sign-up code that was available, and we will now make 7 different models and see how it goes. So as you can see the visual representation, the general the general the bar plot shows the general model performance model provides the best balance of simplicity and performance. It is nearly as well as these sign-up models without any overhead. As you can see, this is the RMSE of the sino-specific models and R square of the sino-specific models. On the right hand side, you can see the difference of the improvement. As you can see, if it's on the positive side, it means it's better, and it's on the negative side, it means it's worse. Same goes for the R square as well. In numerical figures, you can see that once we train the random forest model for each sign-up code using backward feature elimination, we compared performance of sino-specific models against general radio frequency model, and the metrics evaluated are as follows. The RMC means, once again, RMC, the lower the better, and the R square, the higher the better. As we can see there, the R squares showed mixed results, indicating potential overfitting or insufficient data for some sign-up codes. Well, sign-up models for generally improve RMSE over the general model. Some cases it was very significant. And comparing with the general model, we can see that some sign-up code performs significantly better than the general model, while others had no improvement, likely due to data limitation, which could be blamed on the data set or downsampling. Now coming towards the feature selection frequency across the sign-up code, we can see these features had how much how much importance they give contributing to the feature selections, and we can as we can see that when we analyze the features, we can see which is feature selected across all sign-up specific models. And top selected features included absolute humidity, which was most frequently used. Visibility, temperature, and intensity were also very common. Event-related features were least selected. Visuals, um, as you can see in the bar chart, which features were more selected and which features were very less selected. That happens to be the wind-related features. Some features are universally important across sign-up models, which is once again the humidity features. And in sign-up specific variations, we can see different location patterns, different weather conditions. Now it's time to compare the method one, that is per sign-up code, versus per method two, that is the hybrid models which we develop with the when we use RFL with the FSO models. We can see that when we trained a separate model for each sign-up code, we had lower RMSE, and when we trained the RFL with the FSO, we can see the higher RMSE but simple implementation and it a higher R square, indicating a better generalization. So we have two conclusions now. The first method gives better accuracy, but the second method gives better generalization. Now it's time for feature evaluation with the Pearson correlation. We can see that Pearson correlation was used to measure the linear relation with the FSO attenuation. The mutual information captures no linear dependency, while the random forest important determines the impact on model prediction. Now, when we talk about our findings, we found that the distance, visibility, and temperature were top ranked across all the three methods. The Pearson correlation results showed weak direct relationships. The mutual information was very high, suggesting non-linear dependency, and random forest identified distance as the most important predictor. Once again, it's time to see the feature importance for the random forest models. We can see distance was the most influential factor for predicting the FSO power loss, significantly higher than the other features. Visibility and temperature were also key predictors, indicating a strong influence on FSO signal loss. Particulate matter and humidity-related features contributed moderately. Wind-related and sign code features have low impact, but doesn't mean they have useful prediction applications. Top-ranked features for distance, visibility, temperature and should be prioritized in modeling, while the low-important features can potentially be removed and to simplify the model without losing performance. Conclusion will be, I would conclude my model by saying that our general models perform extremely well with RMCs under feature selection, reduce overfitting per sign-up models. But on the other hand, per sign-up model had niche advantages. Hybrid pipeline weren't beneficial. Ultimately, the general model with tuned upper parameters and selected features in the best candidate for deployment. Future work, I would say that in future we'll explore temporal modeling using LSTMs to capture time-dependent weather trends and apply transfer learning to low data sign-up codes and deploy this framework in a real-time adaptive hybrid communication system. Thank you so much for listening.